Welcome to this video on assembly language. Assembly is a low-level language that lets us talk directly to the computer's hardware. In this section, we will learn what assembly language is, how it works, and why it is useful. Whether you are new to programming or just curious, this will give you a clear understanding of how computers follow instructions step by step. Assembly language is a low-level programming language that provides direct access to a computer's hardware. Instead of using binary code, it uses mnemonics, symbolic names for operations like move, add, or sub. These instructions are easier to read and write compared to pure binary. Assembly code directly interacts with the hardware, giving programmers precise control over system resources. However, it is processor specific, meaning the syntax and instructions vary between architectures like x86 and ARM. Learning assembly language offers several valuable benefits. First, it allows us to understand computer architecture at a low level, which is essential for grasping how hardware and software interact. It is particularly useful in embedded systems where resources are limited and precise control is necessary. Assembly also helps in optimization and debugging, as you gain deeper insight into how instructions are executed at the processor level. Finally, it provides a strong foundation for understanding machine language, making you a more effective programmer and systems engineer. Assembly language instructions are grouped based on the kind of operation they perform. These include data transfer, arithmetic, logical, bit manipulation, control, and branching operations. Each instruction uses a mnemonic that directly maps to a machine level operation. Data transfer instructions are used to move data between registers, memory, and input-output devices. For example, move transfers data from one location to another. LDA and STA are used for loading data from memory and storing it back. Stack-related operations like push and pop help with subroutine handling and temporary storage. Instructions like in and out allow communication with input-output devices, making them essential in embedded systems. Arithmetic and logical instructions perform fundamental data processing tasks. Arithmetic instructions include add, sub, increment, and decrement, which deal with calculations. Logical instructions like AND, OR, XOR, and NOT operate at the bit level and are widely used in decision making and control structures. These instructions often affect flags in the status register, which can influence subsequent program flow. Bit manipulation instructions deal with modifying individual bits or group of bits. Clear bits sets them and complements them. These are particularly useful in device control, toggling features, and flag manipulation. Such precise control is one of the key reasons assembly language is used in hardware interfacing and low-level programming. Shift instructions move bits within a register. Logical shifts like SHL and SHR are used for unsigned numbers, while arithmetic shifts such as SAL and SAR preserve the signed bit for signed numbers. Rotate instructions like ROL and RORs cycle bits through the carry flag. These are used in operations like manipulation by powers of 2 or circular buffering. Program control instructions direct the flow of execution in an assembly language program. The JMP instruction performs an unconditional jump to a specific address, altering the program's normal sequence. Call is used to invoke a subroutine and RET returns control to the point where the subroutine was called. These instructions are fundamental for implementing modular code, function calls, and structured program flow. Branching instructions allow conditional execution based on the status of specific flags in the processor status register. For example, BZ branches if the 0 flag is set, BNZ branches if it is not, and instructions like BC and BM depend on carry or minus flags. These are vital for decision making in assembly programs, enabling loops, conditional blocks, and error checking mechanisms. In assembly language programming, registers are the CPU's high-speed storage locations. They temporarily hold data and addresses, making program execution faster. Registers are grouped by function. General purpose registers AX, BX, CX, and DX are used for arithmetic, logic, and data transfer tasks. Next, we have pointer and index registers SI, DI, SP, and BP, which help manage data locations, stack operation, and memory access. Finally, segment registers CS, DS, SS, and ES store the starting address of the memory segments, helping the CPU organize code, data, and stack. Together, these registers are the CPU's toolhead, enabling fast and efficient execution of assembly instructions. In assembly language, addressing modes define how we access data for our instructions. The immediate mode directly gives the value in the instructions. For example, move AL, 5 loads the value 5 into the AL register. In register mode, the data comes from the another register. For instance, move AL, BL copies the value from BL into AL. The direct mode specifies the exact memory address. In move AL 1234H within square bracket, the data is taken from the memory location 1234H. Finally, in indirect mode, the address is stored in a register. For example, move AX, BX in square bracket uses BX to point to the memory location from which the data is fetched. These addressing modes gives assembly programmers flexibility in how they store, retrieve, and manipulate data. This is a simple example of an addition program in assembly language. The instruction move AL, 04H loads the hexadecimal value 4 into the AL register. Then add AL, 0 to H adds the value 2 to it. After this instruction is executed, the value in the AL register becomes 6. The example shows how we use the move instruction to load the data and the add instruction to perform arithmetic operations directly on the register. It is a basic yet powerful demonstration of how assembly language interacts with the processor at a very low level. Here is a comparison. Assembly has low readability and portability but provides high speed and direct control over hardware. High level languages, on the other hand, are easy to write and portable but don't give you as much low level control. Both have their places in software development, assembly is a great when you need speed or precision, while high-level languages are best for rapid development and maintenance. Assembly language is widely used in systems where performance and hardware control are critical. It is essential in embedded systems where low-level programming ensures efficiency. In operating system development, it enables direct interaction with the hardware components. Assembly is also used to write BIOS and firmware, providing the essential code to initialize hardware. Game engines may use assembly to optimize performance in critical sections. Lastly, it is invaluable in reverse engineering, where understanding compiled machine code helps analyze or defect software.